Hello everyone. My name is Yin Ding, a PhD student at Binghamton University. The title of our paper is Learning to Ground Objects for Robot Task and Motion Planning. Robots that operate in the real world need to plan at both task and motion levels. At the task level, the robot generates a sequence of symbolic actions in a discrete space to achieve long-term goals. At the motion level, the robot computes trajectories in a continuous space to implement the generated symbolic actions. Generally, planning algorithms assume that a complete world model is provided beforehand. However, many real-world scenarios are very complex, which means that it is hardly possible to model all objects' properties at planning time. What's more, in such scenarios, modeling robot multi-object interactions is even more challenging. In our work, we consider a stack and push domain, where the robot repeatedly builds a block tower and then pushes it to a goal area. In this task, the robot does not know block size and weight. Our objective is to move blocks from an initial area to a goal area as quickly and stably as possible. It is not easy to address this problem, because planning at the motion level highly depends on the estimation of object properties. Now, let's see two video examples. In these videos, the robot is trying to grasp the block, but the robot does not know the exact object size. Thus, sometimes, the grasping succeeds. Sometimes the grasping fails because the robot cannot know where to place the gripper for grasping. The task-level strategy further depends on the robot's motion-level performance. There are at least 3 plans to move blocks to the goal area in this case. The robot needs to decide which one to take at the task level. This figure shows the overview of the TMOC algorithm, which consists of 3 components. The object properties are unknown, which estimates the size of moving blocks. The state mapping function is unknown, which decides where to place the gripper for grasping. The transition function is unknown, which indicates how reliable an action is. TMOC learns these 3 unknown components in each iteration using task completion experience. To learn these 3 components, our TMOC algorithm first grounds object properties in a high-fidelity physics engine. Then, our TMOC robot learns object properties from task completion experience. Our TMOC robot next improves the task motion planning skills with the learned properties and action completion experience. We have evaluated TMOC in both simulation and the real world. In the simulation, the task is that a robot gripper uses a container to move blocks to a goal area. The simulation platform is PyBox 2D. The right figure shows the experimental results of 4 algorithms. The x-axis is the training episode, and the y-axis refers to the cumulative utility obtained by the real robot. From the results, we get the important observation that our TMOC performs better than the baselines in terms of cumulative utility and learning rate. TMOC was also evaluated using a UR5E robotic arm. In the experiment setting, the robot stacked blocks and then pushed them to a goal area. In this video, the robot tried to stack 5 blocks and then pushes them to the goal area. Though Plan 1 is the most efficient, TMOC found it's very hard for the robot to succeed in pushing a stack of 5 blocks. This is because 2 high stacks are extremely unstable. Compared with Plan 1, Plan 2 has a little higher cost, but TMOC found that pushing 4 blocks are less unstable. Sometimes it may succeed and sometimes it may fail. Compared with Plan 2, TMOC found that pushing 3 or 2 blocks has much higher stability in Plan 3. With dozens of trials, our TMOC robot learned a good stack and push policy, which resulted in a high utility value. In conclusion, the paper has 2 contributions. The first one is a framework called PPS. PPS includes a physics engine for grounding objects' properties. The second one is an algorithm called TMOC. TMOC addresses a PPS problem with unknown object properties. Thanks for your watching.